Good morning or good evening, depending on where you are. We are going to start the webinar in just a couple of minutes. We'll wait for the last few people to trickle in. So until then, sit tight for a couple of minutes. Thank you. Okay, good morning or good evening, depending on your location. My name is Eitan Lightstone. I'm head of design at ShiftLeft, and we also have Fabian Yamaguchi on the webinar as well, who will be starting a presentation for you guys on our OWASP benchmark. And so at this point, I'd like to pass the microphone over to you, Fabian, and please begin.
All right, good morning. Can you guys hear me?
Yes, loud and clear.
Great. All right, okay. So today we're going to be talking about the OWASP benchmark and the technology that we have here at ShiftLeft called the code property graph, which we recently applied to this benchmark to essentially get a measurement of how good our static analysis is. Just a second. Oh, there we go. Okay. So the agenda is going to be, first we'll present this benchmark, and I'm actually going to go a lot into the technical details of the benchmark. Once we've established what actually needs to be solved, we will look at the code property graph and then the results that we've achieved on this benchmark. I'm then going to pass it over to Eitan again, and Eitan is going to talk a bit about how this matters in modern software development life cycles. And finally, Eitan is going to be giving a demo of ShiftLeft. So the OWASP benchmark, what is it? So the OWASP organization is the Open Web Application Security Project. We are not affiliated with these guys in any way. What they do is, well, what they did with this benchmark is they essentially created a test suite of samples that are both vulnerable and non-vulnerable, and you can use these test cases to evaluate how good your static analysis tool is. If you look into the details of that benchmark, then you will see that there are 11 categories, and there's a very clear focus on injection vulnerabilities. I guess that also makes a lot of sense because injection vulnerabilities in web applications are really one of the primary security problems we face in the code today. So you will find command injection vulnerabilities, SQL injection, LDAP, XPath injections, and then there's CrossSite Scripting and path traversal. And in a way, at least from a program analysis point of view, these are also injection vulnerabilities. In the one case, somebody's injecting JavaScript code that will eventually be executed on the browser side, and in the other case, you are injecting file paths to essentially read files off the remote. Then there are 3 categories around usage of weak algorithms. So you'll see hashing functions used in insecure hashing functions been used, like MD5, for example. You'll also see weak cryptographic functions used, and finally weak randomness. And then there are 2 that kind of don't fall into any of these categories. One is about whether cookies are set to be secure, and the other is called trust boundary violation. won't go too much into that right now. Overall, we have 1,415 vulnerable samples in that benchmark, and then 1,325 non-vulnerable ones. And this is the split over the different categories. So P is the vulnerable samples, while N is the number of non-vulnerable samples. And so you can see the categories don't necessarily have the same size. So for example, when you look at XPath injection, you only have 15 positive and 20 negative samples. And then in contrast for SQL injection, there are 272 positive and 232 negative samples. So how do you then evaluate? Well, given that you know for each of the samples whether it's vulnerable or not, you can start measuring what's called the true positive, the number of true positives. Those are the vulnerabilities that you correctly identified. Then there are false positives. Those are things that you marked as vulnerable, even though they're not vulnerable. And then once you have those numbers, you can calculate rates from this. So you can calculate a true positive rate, which is essentially the number of true positives divided by the overall number of positive samples. So which fraction of the positive samples were you able to identify? And then there's a false positive rate, which is analogically the FP rate divided by the the FPs divided by the number of negative samples. And then just to make things very simple, what happens in the OWASP benchmark is that a final score is calculated by subtracting the false positive rate from the true positive rate. So in the optimal case, you would get a score of 100, meaning you have 100% true positive rate. You were able to identify everything, and you have not a single false positive. Right. So let's look at the different challenges that we need to address in order to get a good score on this benchmark. So the first thing is we need to be able to do data flow tracking. So you see this very long chain of different transformations on data here. And in the beginning of this snippet, param is known to be tainted by the attacker, so controlled by the attacker. And then the question is, in the end, is bar actually controlled by the attacker as well? And yeah, looking at this, you might not immediately see it, but in this case, the answer is yes. Now you actually need to prove that you're doing data flow tracking, because there are similar samples where essentially right before the flow ends, you'll see a constant being written into the variable, essentially stopping the flow. So they're really checking, are you tracking the flow or are you just ignoring the propagators, essentially? Then another thing you need to be able to deal with is the typical escaping and sanitization routines found in Java web applications. So for example, CrossSite scripting only exists if the attacker-controlled data is not encoded for use in an HTML context. If it is encoded for use in HTML context, then the attacker cannot inject JavaScript code, and so you do not have a vulnerability there. Right. Then you need to be able to handle collections correctly. So you'll see a lot of code where essentially things are written into collections and then retrieved back from collections. And you need to understand these routines in order to track the flow at that point. Then one of the things that is often the case for static analyzers is that if you have too deeply nested code, too many loops, and in particular unbounded loops, then a lot of these analyzers will simply take very long or, well, not terminate in a reasonable amount of time. So you need to be able to deal with these kinds of constructs as well, where essentially data is propagated inside a loop, and at some point there's a way for the tainted data to leave the loop and essentially end up in a variable that is then passed to some sensitive operation. You also need to be able to track data across interface methods. So let's say you have an object called thing and you call a method called do something on that. Well, then you actually need to trace back to see that do something is created by this factory. And then if you look into the factory, you'll see what kind of object this is. And only if you know that, you actually know where this call to do something goes and whether or not it propagates the attacker control from param to bar here. So this is something that's typically solved in static analysis using what's called points to analysis, but there are also some variations of this, and we implement a variation to do this. Then it checks for configuration files. So you need to be able to read at least basic Java configuration property files. So here, as an example, an algorithm is being initialized to use as a hashing function. And well, you might think that it's always going to be SHA-5 and decide that, okay, that's that's enough for me or not. But actually, it's retrieving a property from a text file. And that might be something like MD5. So you need to read out the configuration file, somehow model it. Otherwise, you cannot win in this benchmark. And finally, I mean, there are a lot more, I think, but this should be the most important ones. They are checking for basic abilities to do constant propagation and some math on integers. So here you have some sample code where there's a condition that is always true. But to determine that, you actually need to reason about this value num here, and you need to trace that num is actually 106, and then carry out this calculation to find that, oh, okay, this number is always bigger than 200, so I'm always going to end up in this branch, and the taint is not propagated. So I hope this gives you an idea of the kind of challenges that are in there. And I guess also that these are primarily challenges that static analysis suffers under. Now, the question is, how do you create a code representation to deal with all these kinds of different elements of code? And can we somehow combine them to actually look at multiple of these properties and decide based on those, is this a vulnerability or not? And this is where the code property graph comes into play. So the code property graph is actually something that we've built a long time ago. The basic concept was already introduced in 2014. And back then, the overall idea was, let's take the typical kind of program representations that you have at the compiler level and essentially just stitch them together in what's called a property graph. So property graph is a graph, so nodes and edges, where the edges are labeled so that you can represent different kinds of relationships within a single graph. And then finally, within the nodes, you can store information in the form of key value pairs. So here you see a code property graph from back then, and all that was merged there were abstract syntax tree edges, so information on what the code looks like, then CFG edges, so control flow information, and then finally some data flow information. And we took all of this and put it into a graph database and essentially created a small query language on top of that that will allow you to formulate questions such as, are there any methods called sync and they have parameters that are reachable by methods called source? Today, the code property graph is a bit more evolved. So today it's a multi-layered code representation, and I'm going to talk about the different layers now. On the lowest level, you have what we already had in 2014. it's just that now it is no longer just for one programming language, but it's actually a representation that we use across multiple programming languages. On that layer, you have the syntax information, control flow information, and semantics about the instructions, in particular data flow semantics. Based on that, we calculate data flows. Based on those, we calculate high-level information flows, and I'm going to go into what that means in a minute. And we then take those high-level information flows and apply policies to essentially point out vulnerable flows versus non-vulnerable flows. So the first ingredient, I would say, for beating the OWASP benchmark is you need a state-of-the-art data flow tracker. And so this data flow tracker, this operates on the lowest level of the code property graph. So it needs a control flow graph essentially, and it needs the taint semantics, meaning you need a description of how these different methods propagate attacker-controlled data. Well, we essentially put together everything that you need today to have a state-of-the-art data flow tracker. It's interprocedural, it's flow sensitive, context sensitive, field sensitive, and in addition to that, we implemented a whole bunch of heuristics that are simply necessary to terminate on time. The benchmark is processed in under 10 minutes. Yeah, I guess that's well, that is essentially something that we need to do because in our use case, our data flow tracker is used per commit within a CI/CD cycle. Yeah, so this operates on the lowest layer of the code property graph, and actually a lot of the information that we put on the layer above can be calculated in parallel. Then, well, essentially you calculate them in passes, such as the passes of a compiler. And we can put these different passes on different cloud instances and then put them together again. So it's kind of like a data structure for code analysis in the cloud. For the benchmark, this is not so relevant because this is not a huge application. It's yeah, well, it's not small, but it's not as big as you would see with the usual customer code. So now that we have these data flows, we do something that I think is novel. We actually stitch together these low-level data flows to create what we call high-level information flows. And the idea is, well, let's consider this example here. So here the attacker controls the request, and then by controlling the request also controls this map here, and then controls this this array values, and then controls param. This is escaped, put into some sort of array again, and eventually reaches a printf call. Now, ignore the escaping for a bit, but overall, this is the primary flow of information that goes from an HTTP request into a printf routine. Now, that's actually not enough to decide whether this is a CrossSite scripting or not. What you additionally need is you need to find out where does this printf actually go. And so to do that, you would need to consider a second flow, which is the flow of the response. So here you see that response is actually set to content type text HTML. If that were not the case, then this would not be a CrossSite scripting vulnerability, ignoring the escaping there for a moment. So we actually have two data flows that we need to put together in order to recognize that this is a high-level flow from HTTP back to an HTML document. And so once we have extracted these high-level flows, what we can do is formulate policy on these flows. So for the CrossSite scripting example highlighted in bold here, we would formulate a policy that essentially says, if there's a flow from HTTP to a print routine that also goes out via HTTP plus HTML possibly, then and the data on the way is not encrypted, and it is not hashed, and it is not escaped, and it is not encoded, then we call this a cross-site scripting vulnerability. And here you can see these policy rules for the 11 classes. Well, you can see that essentially we are able to fit the description, the policy that you would use for the vulnerability classes onto this one slide. Okay, so for the results, first thing to point out is that our analyzer found all of the positive cases. So the true positive rate is 100%. And then the false positive rate on average is 25%. If you actually look over all samples, then the average is 22%. The difference here is that in the official calculation of the OWASP benchmark scores, what you do is you simply average these rates here. So you average the true positive rate and you average the false positive rate. What that means is that each category counts equally, even if a category only has few samples. And the score you see below here, this is what you get if you well, if each sample essentially counts the same. So official OWASP score is then 0.75, while the Y index, if you calculate over all samples, is 0.78. So here's a little table showing how this compares to other tools. You can see some commercial static analyzers here. We don't really know which one is which, so this is anonymized, but we do know that these SAST tools listed here include the big players essentially in the market, which is Checkmarx, HP Fortify, Veracode, and IBM AppScan. Yeah. So we are at 0.75, and I think the best commercial one, 0.33. Yeah. Okay. So we also analyzed the false positives to find out whether we can do something about them and also how our analyzer performs overall. We found that the OWASP benchmark is essentially constructed from different building blocks, and each of the false positives was due to one of these three building blocks here. So this is the building block you see on the left in the upper corner. This is where we essentially overtaint collections, meaning if a collection is somehow tainted by an attacker, then we consider the entire collection tainted and not just the constant field that was tainted. So if there is a constant, then well, it makes a lot of sense to actually look at this constant and be sensitive to this. However, in the general case, this is not a constant. So in that case, it's very hard to essentially get rid of the false positive here. Then there's another case where one would need to model the behavior of lists. So here something safe is added, something unsafe is added, something safe is added again. The first safe entry is removed, and then finally the last entry is used, and that is also safe. So that's why actually there's no attacker controlled data propagating from the value list to bar. And then finally, yeah, I guess this is a bit artificial, but consider that there's string ABC, and we always read the second character B. Then we know that all of these branches here in the switch statement are actually dead, and so bar is always going to be set to Bob. And this is the third case in which we have false positives. Okay, so looking at the larger context, what does this all mean? Well, these remaining false positives, they could be addressed via these CPG passes as well. But I'll honestly say that we're not going to do that. That's simply because it's in the general case, this is computationally very expensive. And I think usually what will happen is that the results you actually get on customer code are more or less the same, but it takes much longer to produce them. Another important thing to understand about the setting we work in, our product doesn't report these findings to an analyst only to look at those, but instead it uses this information to instrument a runtime agent. And so here it is much more important to be comprehensive. So to identify all the flows that look like they should be protected, and then still at runtime we can see whether these flows can actually be triggered and filter false positives there at a much lower cost. So what was relevant for us here was to essentially achieve the 100% true positive rate on the benchmark. All right. So with that, what do we do, Ethan? I give this to you, or questions now, or?
Yeah, let's move on to, I guess, my part of the presentation.
All right.
And
Okay,
I will
cool.
also steal presentation mode from you. So I will make myself presenter. There we go. So feel free to mute yourself, Fabian, for now.
All right, thank you.
Share my screen. Main screen. Okay, so right about now you should be seeing my screen. And present. So yeah, thank you, Fabian. That was a fascinating run through of our technology and the effect on the OWASP benchmark. I just want to point out to anyone who's listening right now or watching, we will be taking questions at the end. So I'm going to just go through a couple more slides fairly quickly and then a quick demo of the ShiftLeft experience. And then we'll take some questions and then end the webinar. So feel free to use the built-in GoToMeeting system to ask questions at any time, and we'll check those out at the end. So I'd like to talk about why everything we've been explaining to you this morning matters in modern software development life cycles. So as you can imagine, modern software, has introduced a lot of challenges into the security ecosystem. For one, faster release cycles and microservice architecture has really put a strain on what I would describe as legacy or existing security solutions. Adoption of open source libraries. Obviously, the more custom software that's being written, the more that software is including third-party libraries and frameworks to help accelerate things. And that makes it very difficult to understand how you have been introducing vulnerabilities into your software by using those libraries, and are you using them in a way that's secure or insecure? It's very difficult to tell sometimes. And of course, a lot of the security tooling out there is threat-based. So if you're mostly focusing on attacks, which we call whack-a-mole, obviously that's very reactive, and of course it's very expensive because it can involve a lot of human overhead to tune that correctly, and expensive operationally as well, depending on how it interfaces with your network layer. And finally, lack of data visibility in microservices. So the more your software is spread out as interconnected services, the more difficult it can be to understand whether you're using sensitive data in a secure manner between those microservices, and where exactly does sensitive data reside in your architecture. It's a harder problem to solve. And finally, the DevOps mentality itself, or the DevOps process, is starting to erode traditional app security. So for example, there's development and there's production. And in development, there are a variety of tools just focused on that side, like DAST and IAST and SAST, analysis of code. And of course, in production, other tools are used, like web application firewalls, and you have a SOC. And the issue with this is, oh, that built pretty quickly. I guess it just builds all at once here. So correlating vulnerabilities is difficult, and threats together. So in other words, vulnerabilities on one side, threats on the other side, but it's very difficult to connect those two worlds in an automated way or efficiently. Security has trouble keeping up with aggressive release cycles. And finally, operational costs are quite high. especially because you're buying a variety of tools that live in these two worlds, and each requires maintenance. So at ShiftLeft, we believe in a continuous security model that's more of a natural fit for the CI/CD workflows that people have in modern dev shops. And so, of course, we have a two-pronged solution. One of them, Fab's got into some detail on, where we perform an analysis at the code level. And that analysis is very efficient and modern in how it helps surface security problems in the software. And in production, we have a runtime solution as well, which protects that software at runtime. And the interesting thing about this technology is it's really one solution, but two-pronged. In other words, they feed each other. So the development side, where we have the analyzer, while it does surface security insights from the analysis phase, that analysis also automatically configures the runtime agent that runs with the software and protects it from threats in production. And what this helps you do ultimately is, while technically you are now protected at runtime, it allows the runtime activity to help further strengthen how you decide to secure things on the code side, where now you have a really clear way, when you have knowledge of what you have from analysis and how things are being impacted in production, you have a really clear way to prioritize vulnerabilities. And one of the things that I've noticed is a lot of dev shops are using code analyzers, but they come up with a ton of results, and it's very difficult to understand where to begin, or what's worth focusing on or not, or should I bug the developers with this? Okay, so let me move on to the ShiftLeft demo. So let me just see, I'm going to escape full screen mode here and move on to the product dashboard. Okay, so what I've done already here is I've prepared one application called Hello ShiftLeft, which I'm currently monitoring with ShiftLeft. And I've just logged in here. And so this is the main dashboard, where I would see all the applications that are being analyzed and monitored by ShiftLeft. So one thing I'll point out is, as I go through this experience, I want you to keep in mind that the security insights that are being visualized here, they're really a hybrid of information that has been derived from code analysis, as well as all the context at runtime in terms of activity and attacks. So let me click into this application. And what I'll do is walk you through what this summary is, and then get in quickly into a one or two use cases. So right now we're on the app summary view, as what we call it, for Hello ShiftLeft. And the first thing we'll see here is a throughput chart showing some activity that I've triggered on this application over the last hour. So we have this drop down here. And so what you can see here is when I first initialized the app and exercised a few parts of it with my web browser, immediately we have some security, what we call violations or problems that have been detected in runtime. And if we keep going, I'll go kind of clockwise, not quite clockwise, counterclockwise. On the left-hand side, we have a panel that we call triggers. Triggers are what we've determined triggers of any data flows in the application. And so really the way that we have figured out vulnerabilities and the way we present a lot of information is ultimately about data flows within the application, because a data flow involves an input from the outside world. That input goes through a variety of transformations or method calls, and then that input potentially involves a query or a store out to a data sink. And that is the analysis of that data flow helps us understand whether that particular flow is a vulnerable one, or is that flow doing something inappropriate with sensitive data, which I'll get into in a moment. So this trigger is really how these flows are triggered in this application. Because this is a web application, these triggers will look like normal URL routes into the app. And so if it's not a web-based application, the triggers will look a little different. They'll be named based on method calls inside the application. And so of course we see some fairly recognizable triggers, like a customer being retrieved here in this URL. This one maybe shows an account. And the highlight is based on just regular throughput on those various triggers of the application. On the right-hand side, we have a panel called Data Destinations. And what this is showing is how data that we've automatically classified inside the application. And so the way we the way that the data is classified and which data sinks it's going to. And I'll describe how that works in a moment. But what I can tell you is right away I can see that data that's been classified as account data or payment data is being sent back out to the web. So this is an interactive web app where, of course, it's receiving inputs from the web and saving data back out to the web to display it. And if I continue here, you'll see another data sync, the logging system. And we see a variety of categories of data that are being saved to a logging system. And some of these obviously have red highlights because this is considered inappropriate use of payment data, for example, that's being saved to the log. And so I'll click into this in a moment, but I'll just also first explain this this little panel here called violations grouped by OWASP. So this widget is effectively summarizing all all security insights that have been picked up by code, which is this column here, as well as all of those security issues in code that we've seen happening in runtime. So in other words, in the case of this top category called injection, we can tell that there are 76 locations or data flows within this single application where an injection attack is possible, or there's an injection vulnerability, I should say. And then one of those locations has actually been attacked in runtime. And depending on the configuration of the ShiftLeft agent, that attack can be blocked by default, or it can be in observation mode where it doesn't block anything by default. So let me quickly get into a use case about this payment data and describe how we understand the data as well within these data flows. So if I drill in on payment data, I'm just going to click this. It adds a couple of filters here to the top of the screen. So one is now we're showing the app summary view for all triggers and data destinations involving log as a destination data sync and payment data as a sensitive data category. And if you look at the right panel now, we see a list of individual data variables, in this case Java variable names, because this is a Java app, that are being saved out to log. And the way that we detect this is we semantically understand using natural language processing what variables you have in the source code, as opposed to trying to interpret the data in transit in runtime, which is much more operationally expensive and has more false positives. So in this case, as our analysis ran, we pick up variable names like account number, and through natural language processing, we automatically determine account number is a kind of payment data. And so then we monitor in runtime the appropriate endpoints of the application to infer that that account number is actually being saved out in production. And so that's why these blue highlights are here, where we see some of these pieces of data actually successfully being saved to log, and then some of them aren't. So in other words, account down here has no runtime activity. So you can imagine if a developer has accidentally left some debug code into their software, sometimes that debug code will have a condition around it which will ensure that it never actually happens in production. So that may be what happened with account, where it's possible in the code, but it hasn't happened yet in runtime. So I can't tell you at this point whether that's because a customer just hasn't exercised this app the right way that would invoke this, or perhaps there's a condition which will never be true, and account will never be saved. In these other cases, I would prioritize these. So it's quite alarming to me that account number up here is being saved out to log, implied by the code, but also it is truly happening at runtime. So I'm going to click into this, and now we're at the deepest level of depth of looking at an individual data flow in this case, where from top to bottom we see a particular method trigger that was invoked from that from a web route, I believe. And here is account number, which we showed you earlier, where it receives the account, initializes it as account number, and then it passes through a variety of method calls. And as it goes through, you'll notice that it is renamed or assigned to different parameters until finally at the very bottom, it's saved by the logging system via the info call on logger, where it's received as param1, which we know because of the analysis that was from that was account number assigned to that. And so that's how it's logged out. And this is a pretty unprecedented blend of experiences, in my opinion, because what we started out with was an operational view. At the app summary view, where at a high level we see what security issues are happening, both detected at code time, but also witnessed at runtime. But finally here we get to a depth where we see line of code visibility into exactly how a security issue happens in the code. And I could cut and paste this presumably into a Jira ticket and get a developer involved to fix it if I believe it's worth fixing or it's high priority. So let me wrap up the demo. I'll show one more thing here. So let me go back to the app summary view. And in addition to monitoring your application in this kind of view, there's also other maybe sort of higher level views into what's going on from a security standpoint across the whole organization. So if I back out and go to our app dashboard, one thing you can do is go to the alerting system over here. And these are all the alerts that have been triggered, and we'll send out notification emails when security incidents happen. I won't go into those, but I will show the violations list. And so this is effectively a master list of all security issues that have been detected from analysis across all applications in this case. Of course, we only have one application in this particular account. And if I go through these, you'll see that for each of these security issues, some of them are vulnerabilities. In this case, we have command injection, and some of them are data leaks over here. And what I can do is actually sort this list by number of incidents. And this is a verbiage for when we see runtime activity or attacks related to this vulnerability. So I've sorted by this, and we can see 427 runtime incidents have occurred for this particular problem that was detected. And so, we can go look at an injection attack, of course. Let's go look at, this kind of injection attack. And although nothing has happened at runtime yet for this one, what we can do is visit a particular violation and understand what it is. Down here, we have a data flow that describes this particular vulnerability. That is an injection involving the expression framework in Spring, the expression parser, excuse me, that's part of the Spring framework, which could presumably invoke arbitrary commands. And so if this is alarming to me, despite it not happening at runtime yet, I'm free to assign this to someone. So I can click assign, and there's some basic, project management tooling effectively in here that allow you to collaborate with other teammates and assign them to each other and mark them fixed. And so I think that concludes the demo for the purpose of this webinar. One thing I'll probably leave with before we get to Q&A is, this isn't sort of a one-time thing because of the efficiency of this approach and the analysis in particular. This is an ongoing real-time way to really track the evolution of security for this application. So not just at a glance understand its problems, but this cleanly fits based on our insertion approach into a rapid development process where every time a new version of this application is prepared and deployed, analysis can be run very quickly, and you can right away see those results every time that this app is analyzed. And shortly we'll have an experience around tracking these violations from release to release, so in more of a dashboard view, which I'm very excited about. Okay, so let me get back to the slide deck. So one thing I want to point out is there is some reading material that we've provided along with this webinar, which I believe is accessible to you through the GoToMeeting panel. Yes, they're in the handout section, if you can find that in the GoToMeeting panel. You'll only be able to get access to those while inside the meeting, I want to point out. So grab them if you can, where there's a white paper describing a lot of the technologies that Fabian and myself have described. And there's also an offering for a free GDPR data assessment. So one of the things we can do is produce a sort of comprehensive PDF describing the flow of all data in your software, or at least for one application for free. So using this technology, we can create that PDF for you and give you that report. So please feel free to get those items from the GoToMeeting handout section. Okay, well, that's not, well, there should be a slide that says Q&A, but basically at this point, I'd love to take your questions. So I'm gonna have a look. Okay, so one of the questions that's come up, which I'll take, is who is the typical audience for ShiftLeft? Is it, is the user meant to be security, DevOps, or engineering? So I'll take a crack at that. It's actually kind of a difficult question to answer as the designer, one of the designers working on this. It's certainly top of mind, who is the persona or who are the personas that are meant to use it? And this has been a struggle, but I also think an opportunity. Right now, I would say the tool is primarily a bridge between security and DevOps. And of course, we're shooting for the emergence of a formal role around DevSecOps, where we have security people embedded much closer to development teams. But the answer is all three to a certain extent. So I think at the highest level, where you're managing alerts and policies, that there is likely a high-ranking leader or a security persona that is looking at all issues across all applications, managing alerts and so on, and managing the policy that drives what is determined to be a red alert or a yellow alert and so on. And then of course, you'll have someone maybe closer to DevOps who's focused on individual applications and potentially monitoring those like they would with an APM tool, but they're looking at any security issues that pop up specific to an application, so that might be the app summary view. And finally, the developer, likely isn't using a tool like this every day, but when there is something assigned to them, they could potentially come into the experience and look at a data flow describing a particular vulnerability and deal with that with pull request or the next release. So hopefully I've answered that. Let me see what else we can find. Okay, here's a good one. One is, so what if my variable names aren't detected by the natural language processing or semantic thing? So yeah, if you recall in the demo, when I looked at one of the data leaks, it automatically identified something called account number, and it classified it as a variable that's sensitive. Maybe I'll pass this one to Fabian. So Fabian, why don't you answer this one? What happens if there is a variable specific to my code? It's not automatically recognized. What do I do? What happens with ShiftLeft there?
I showed you this policy language earlier, which you can use to describe the flows that are relevant to your organization. In addition to being able to describe the endpoints of data and the transformations on that data, you can also describe what your variable names look like. So if you have if your developer tends to name their the passwords that they propagate foo or bar, then you can actually put this into your policy to monitor for that. Of course, for the product comes with a default policy that hopefully covers let's say the usual cases. But if there are such naming conventions, then they can be covered by additional policy rules.
Great, thank you, Fabian. another question I'm looking at here, what is the impact on my runtime performance speed? So that's a common one that we get, and a good one. So what I mentioned is the sort of the two-pronged insertion approach. So one was the code analysis side, and the other is in runtime we use a runtime agent, an agent-based approach. There are slight differences depending on which language the agent is for. In the case of Java, which I personally am most familiar with, that agent runs inside the JVM with the application. Very similar to APM solutions like New Relic or AppDynamics, the way their Java agents would work and automatically instrument a running application. And the good news is in our case, unlike certain security solutions as APM as well, our agent is quite a bit more efficient. I don't have an exact number for you. I believe it's in the order of magnitude of maybe 10 or 20 times more efficient than an APM agent. So it's basically minimal. And the reason for that is how the handshake happens between the analysis side and the runtime side. So if you deployed an average security agent or an average APM agent on an application, it basically has to instrument almost everything. And if the if the performance plummets, it's really up to you to sort of configure it to instrument less so that it's not tanking the performance of the application. In the case of ShiftLeft's microagent is what we call it. It's very lightweight and it only instruments what it needs to. So the analysis will inform it of which endpoints are determined to be sensitive or vulnerable. And so the ShiftLeft agent only needs to automatically instrument those endpoints. And in particular, if it's looking for patterns of attack, if you use sort of a standard RASP solution, it will monitor for that attack across all parts of the application that lead to database queries. But in our case, we can limit that just to what we know are the vulnerable pathways, effectively. So long story short, it's a minimal performance impact there. So let me just get back to the questions here. I'll probably take one or two more and then we're going to wrap it up. Okay, so next question is, what languages does ShiftLeft support? So right now we support Java and .NET, and on our roadmap, I believe coming up next is going to be JavaScript soon and Golang. Fabian, do you know more about? Am I speaking the truth here in terms of the exact roadmap?
That's correct. I think Golang is further ahead as JavaScript.
Okay.
Yeah, but overall, that's correct. Yes.
All right. Thank you. Okay. Last question here. Do you integrate with any bug tracking tools? So the answer to that is not yet. But it is definitely a priority of ours, and in fact, we're building that and we'll be shipping that capability soon. I believe the first one we'll support is Jira, but don't quote me on that. It might be another one, but I'm pretty confident it's Jira. And so the way that will work very soon is, if you remember from the demo, I showed you how you can kind of visit what we call a violation detail, which has some kind of minimal project management capabilities where you can assign it to people and they can mark it fixed. So if you integrate with Jira, that UI will then synchronize with Jira tickets. So you can assign it into Jira, and then I believe that it'll be connected to the Jira ticket. And so it'll be able to get fully managed inside Jira. And then the status of the ticket will also be reflected inside the ShiftLeft dashboard. So very excited about that coming up, I believe in the next, you know what, maybe I shouldn't say an exact date, but soon. Cool. Well, listen, those are all the questions we're going to take today, and we're going to end the webinar. Thank you very much, everyone, for attending. A recording, I should have mentioned that this webinar is being recorded, so I believe you'll get access to the recording afterwards at some point soon. And thank you, Fabian, for your wonderful presentation.
Thank you too, everyone. Bye.
Okay, take care. And now I'll attempt to figure out how to end this webinar. Have a good morning or evening, everybody.